Hello, in this lecture we'll answer on two questions. In the first question, we'll find out the area of this circle that is inside square ABCD. And in the second question, we'll find out the value of the ring area that is inside the quarter circle. We start with the first question. In the drawing, we have square ABCD. Inside square ABCD, we have a circle. We know that this angle CBT equals to 30 degrees. And we also know that line segment PD, this line segment equals to 5 units. And our mission is to find out the area of this circle. Okay, so first of all, we will define the center of this circle as O. We will join points O and P together by a straight line. Point O is the center of the circle, point P is the point of the circle itself, therefore OP is the radius of this circle that we'll define as R. We have here the radius OP that is drawn to the point of tendency, therefore according to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tendency. This angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, we will join points O and Q together by a straight line. Point O is the center of the circle. Point Q is the point of the circle itself, therefore OQ is the radius of the circle that is equal to R. All the angles inside square ABCD are right angles. So this angle, it is a right angle, it is equal to 90 degrees. This angle, it is also a right angle. This is also a right angle. And finally, this angle, it is a right angle, it is equal to 90 degrees. So actually, inside quadrilateral OPAQ, before that, we have the radius OQ that is drawn to the point of tendency. Therefore, according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. So inside quadrilateral OPAQ, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees, plus the size of this fourth angle. In total, the sum of those 4 angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So 270 degrees plus the size of this angle, in total they must be equal to 360 degrees. Therefore, the missing angle must be equal to 90 degrees. In order to complete the sum of the angles in this quadrilateral to 360 degrees, this angle must be equal to 90 degrees. Because 90 degrees plus 270 degrees is 360 degrees. So we found out that inside quadrilateral AQPO we have 4 right angles. Therefore, quadrilateral AQPO is a rectangle. Quadrilateral AQPO is a rectangle because it has 4 right angles. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, side PO equal to side AQ. Again, PO equals to AQ. PO equals to AQ. But we have already found out that PO equals to R. It is the radius of the circle. And from this equation, R equals to PO equals to AQ, we will derive that AQ is also equals to R. And here AQ, it is also equal to R. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we will get that OQ equals to PA. OQ equals to PA or AP. OQ equals to AP, but we already found out that OQ equals to R. It is the radius of the circle. And from this equation, R equals to OQ equals to AP, we will derive that AP is also equals to R. AP equals to R. Here we can write down that AP equals to R. So we actually found out that quadrilateral AQPO is not a rectangle but a square because all of its sides are equal to each other, they are equal to R. Okay? And we also know that in square ABCD, all the sides of square ABCD are equal to each other. That is to say, side AD equals to side AB. AD equals to AB. So AD equals to AB. What is the value of AD? The value of AD equals to 5 plus R. Okay, the value of AD, it is equal to 5 plus R. And what is the value of side AB? The value of side AB equals to R plus QB. R plus QB. So, in conclusion, we found out that 5 plus R equals to R plus QB. Here we subtract R from this equation and we will get that 5 equals to QB, or QB equals to 5 units. So we can write here that side QB equals to 5 units in its length. Here side QB equals to 5 units. In the next step, I will present to you rule number 2 and we implement rule number 2 in our drawing. According to rule number 2, the lengths of two tangents from a common extreme point to a circle are equal. Here we have the common extreme point, point P. From the common extreme point, point P, we have two tangents to the circle, tangent PA and tangent PB. And according to this rule number 2, PA equals to PB. So we actually can implement rule number 2 in our drawing. If we focus on the common extreme point, point B, here, if we focus on the common extreme point, point B, from the common extreme point, point B, we have two tangents to this circle, tangent BQ and tangent here, this point is actually point S. This is point S, it is the point of tendency of tangent BT with this circle. And the second tangent from point B is tangent BS. And according to rule number 2, BQ equals to BS. I'll repeat again. According to rule number 2, BQ equals to BS. But we have already found out that BQ equals to 5 units, so we can write here that BQ equals to 5. And from this equation, 5 equals to BQ equals to BS, we will derive that BS is also equals to 5 units. Okay, BS is also equals to 5 units. BS equals to 5 units. Here, BS equals to 5 units. In the next step, we will join points Q and S together by a straight line. What is the size of this angle? That is actually angle QBS. What is the size of angle QBS? From the drawing, it is very easy to see that the size of this angle QBS equals to the size of the right angle, that is angle ABC, minus the size of this angle, that is 30 degrees. That is to say, 90 degrees minus 30 degrees equals to the size of this angle. So 90 degrees minus 30 degrees, it is 60 degrees. Angle QBS equals to 60 degrees. So if this angle equals to 60 degrees, the other two angles, in total, they must be equal to 180 degrees minus 60 degrees. 180 degrees minus 60 degrees is 120 degrees. Okay. But before that, in triangle QBS, we have two sides that are equal to each other. Those two sides, they are both equal to 5 units, therefore they are equal to each other. QB equals to SB equals to 5 units. And we have the rule that in front of equal sides in a triangle, there are equal lengths. In front of equal sides in the triangle, there are equal angles. So those two angles that are located in front of equal sides must be equal to each other. So if this angle is equal to alpha, then this angle must be also equal to alpha because of the fact that those two angles are located in front of equal sides, therefore they must be equal to each other. So both those two angles, they are equal to alpha. And as I already mentioned before, this angle equals to 60 degrees. Therefore, the sum of the two other angles, those two other angles must be equal to 180 degrees minus 60 degrees. 180 degrees minus 60 degrees is 120 degrees. So it means that alpha plus alpha equals to 120 degrees. I'm writing down. We found out that in triangle QBS, alpha plus alpha must be equal to 180 degrees. Alpha plus alpha is 2 alpha. 2 alpha equals to 180 degrees. Here we divide this equation by 2. So alpha equals to 180 degrees over 2 is 60 degrees. So we found out that angle alpha equals to 60 degrees. This is angle alpha that is equal to 60 degrees. And this is also angle alpha that is also equals to 60 degrees. So actually, inside triangle QBS, we have three angles that are equal to each other. They are all equal to 60 degrees. Therefore, triangle QBS is an equilateral triangle. I'm writing down triangle QBS is an equilateral triangle. Why? Because all of its angles are equal to 60 degrees. And we know that in an equilateral triangle, all the sides are equal to each other. So side QB equals to 5 units, side BS equals to 5 units. Therefore, the third side, the missing side, must be, side QS, must be also equal to 5 units. QS equals to 5 units. In the next step, we will join points O and S together by a straight line. Point O is the center of the circle. Point S is the point of the circle itself. Therefore, OS is the radius of this circle that is equal to R. And we have the radius OS that is drawn to the point of tendency. Therefore, according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. In the next step, I will copy quadrilateral OSBQ, this quadrilateral, in a new page, and we'll analyze quadrilateral OSBQ. Angle OSB, this angle equals to 90 degrees according to rule number 1. Angle OQB also equals to 90 degrees according to rule number 1, of course. finally, we already found out that this angle equals to 60 degrees, angle QBS. So this is actually quadrilateral QBOS that I copied from the original drawing. You know that the sum of the angles in quadrilateral QBOS is equal to 360 degrees. So 360 degrees minus the sum of the three non-angles must be equal to the size of this missing angle, that is actually angle QOS. So I will write it down. 360 degrees, that is the sum of the angles in any quadrilateral, and especially in quadrilateral QBOS, minus the sum of the three angles here, minus 90 degrees, minus 90 degrees, minus 60 degrees. It will be equal to the size of the missing angle, that is actually angle QOS. So 360 degrees minus 90 degrees is minus 180 degrees, and minus 180 degrees minus 60 degrees is minus 240 degrees. And 360 degrees minus 240 degrees, it is equal to 120 degrees. So we found out that the missing angle, angle QOS, is equal to 120 degrees. So we can write down the original drawing that this is the missing angle, that is equal to 120 degrees. Okay, so in the next step I will present to you the law of cosines, and we will implement the law of cosines in the green triangle, triangle QOS. So what is the law of cosines? First of all, the law of cosines is true in any triangle. So if we have a triangle ABC that could be any triangle, so here this is a triangle ABC that could be any triangle. And we know that the length of side AB is A units, the length of side AC is B units, the length of side BC is C units, and the angle between side AB and side AC is theta. Then, according to the law of cosines, C squared equals to A squared plus B squared minus 2 times A times B times cosine theta. I'll repeat again. According to the law of cosines, we get that c squared equals to a squared plus b squared minus 2 times a times b times cosine theta. In the next step, we'll implement the law of cosines in this green triangle, triangle QOS. So I copy triangle QOS in this new page and we'll implement the law of cosines in this triangle. So this is triangle QOS that are copied from the original drawing. So according to the law of cosines, in this triangle QOS, 5 squared equals to r squared plus r squared minus 2 times r times cosine 120 degrees. Again, 5 squared equals to r squared plus r squared minus 2 times r times cosine 120 degrees. 5 squared is 25, r squared plus r squared is 2r squared, and it is equal to minus 2 times r squared minus 2 times r is minus 2 times r squared times cosine 120 degrees. Cosine 120 degrees, it is equal to minus 1/2. So here we have 2 in the numerator and 2 in the denominator, so 2 will get cancelled. We have minus times minus is plus. So in conclusion, we found out that according to the law of cosines, (25) equals to 2r squared plus r squared. So 25 equals to 2r squared plus r squared is 3r squared. So here we divide this equation by 3 and we get that r squared equals to 25 over 3. R squared equals to 25 over 3. And we know that the formula for the area of any circle, it is equal to pi r squared So the formula for the area of our circle is actually pi r squared. So it is pi times r squared. We already found out that r squared equals to 25 over 3. Therefore, we substitute r squared in this formula by 25 over 3. So we actually found out that the area of our circle, the area that we are looking for, it is equal to either 25 pi over 3 square units, or in terms of numbers, it is equal to 50.265 square units. Okay, repeat again. The area of this circle, it is equal to either 25 pi over 3 square units, or in terms of numbers, it is equal to 50.265 square units. We finished with the first question. In the next step, I will present to you the second question, and we will solve the second question in 3 different methods. So, in the drawing, we have a quarter circle. Inside this quarter circle, we have a small circle. It is given us in the question that line segment CD equals to 8 units, and we also know that this angle ACD, it is a right angle, it is equal to 90 degrees, and our mission is to find out the green area, or the size of the green area. So we'll start with the first method, and here in the next step we'll define the center of this small circle as point J. We'll define the point of tendency CD with this circle SE, and we'll define the point of tendency OB with this circle SF. In the next step, we will join points J and D together by a straight line. Point J is the center of the small circle. Point E is the point on the small circle itself. Therefore, JE is the radius of the small circle that we will define as R. And we have the radius JE that is drawn to the point of tendency. Therefore, according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Likewise, we join point J and F together by a straight line. Again, here point J is the center of the circle, point F is the point on the circle itself. Therefore, JF is also the radius of this small circle that is equal to R. And again, we have the radius JF that is drawn to the point of tendency. Therefore, according to rule number 1, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. Here we know that this is a quarter circle. In any quarter circle, point O is always this point that is point O. It is always the center of the quarter circle, and this angle AOB, it must be equal to 90 degrees because of the fact that AOB is a quarter circle. So this angle equals to 90 degrees. And here we know, and also, that AO is the radius of the quarter circle. It is true in any quarter circle. AO here is the radius of the quarter circle, so we'll define the radius of the quarter circle as capital R. Therefore, AO equals to capital R. Okay? And here it is given as the question that line segment CD is a straight line. Line segment CD, it is a straight line. So here, actually, we will focus on AO. AO is the radius of the quarter circle, therefore it is absolutely a straight line. So if we focus on this side of the straight line AO at point C, here the sum of the angles must be equal to 180 degrees, according to the rule number 3, that the sum of the angles on one side of a straight line is equal to 180 degrees. So which angles we have at this side of the straight line AO at point C? We have this angle that is equal to 90 degrees plus the missing angle. In total, the sum of those two angles must be equal to 180 degrees, according to rule number 3. So the missing angle must be also equal to 90 degrees in order to complete the sum of the angles on this side of the straight line AO is point C 280 degrees, this angle must be equal to 90 degrees. Okay, so in the next step, from point J, that is the center of the small circle, we will draw perpendicular on CO. Again, from point J, we will draw perpendicular on CO. So actually, this angle equals to 90 degrees, and this angle it is also equal to 90 degrees according to our construction. We will define the point of tendency of we will define the point of tendency, or we define the touching point of the perpendicular from point J and CO as T. So inside this quadrilateral CTEJ, inside this small quadrilateral, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. Therefore, the fourth angle must be also equal to 90 degrees. In order to complete the sum of the angles in this small quadrilateral to 360 degrees, this angle must be equal to 90 degrees. Likewise, if we focus on the small quadrilateral OTJF, in the lower small quadrilateral OTJF, we have here 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. Therefore, the fourth angle must be also equal to 90 degrees. So here, we'll focus on this angle, angle EJF. Angle EJF is equal to this angle EJF equals to 90 degrees plus 90 degrees, that is 180 degrees. And because of the fact that angle EJF equals to 180 degrees, it means that angle EJF is a straight line. So if angle EJF is a straight line, it means that line segment EJF is a straight line. And if line segment EJF is a straight line, it means that line segment EF is also a straight line. Line segment EF is a straight line. And if line segment EF is a straight line, it means that quadrilateral CEFO is a rectangle. Quadrilateral CEFO, this quadrilateral, is a rectangle. Why? Because it has 4 right angles. It has 4 right angles, therefore it is a rectangle. But we also know that the opposite sides of a rectangle are equal to each other. That is to say, CO equals to EF. In rectangle CEOF, CO equals to EF. CO equals to EF. But we know that EF equals to R plus R, that is 2R. So we can write here that EF equals to 2R. And from this equation, CO equals to EF equals to 2R, we will derive that CO is also equals to 2R. CO equals to 2R. Here, CO equals to 2R. Okay, CO equals to 2R. So in the next step, we'll join points O and D together by a straight line. Point O is the center of the quarter circle. Point D is the point of the quarter circle itself. Therefore, OD is the radius of the quarter circle, that is equal to capital R. So in the next step we will implement the Pythagoras theorem on the right green triangle, triangle OCD. On the right green triangle, triangle OCD, by PT is the relation for Pythagoras theorem. According to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse on this green right triangle, triangle OCD, is equal to OD. Therefore, the square of the hypotenuse is OD squared, and it must be equal to the sum of the squares of the perpendiculars. That is to say, it must be equal to CO squared plus CD squared. I repeat again. In the right green triangle, triangle OCD, according to the Pythagoras theorem, OD square equals to CD square, CO square plus CD square. Okay. CO equals to capital R, therefore CO square is capital R square, and it is equal to CO square. CO, we already found out that CO equals to 2R, therefore CO square is 2R squared, that is 4R squared, plus CD square. CD equals to 8 units according to what is given as the question, therefore CD square is 8 squared, that is 64. So in conclusion, we found out that according to equation number 1, R square equals to 4R square plus 64. Here we subtract 4R square from this equation, equation number 1, and you get that capital R square minus 4R square equals to 64. Okay, we found out that according to equation number 1, capital R square minus 4R square equals to 64. But what is actually the area of the green shape? It's very easy to see from the drawing that the area of the green shape it is equal to the area of the quarter circle minus the area of the small circle. I repeat again, the area of the green shape it is equal to the area of the quarter circle minus the area of the small circle. So the area of the green shape equals to the area of the quarter circle, that is actually equals to pi times capital R square over 4, because the radius of the quarter circle is capital R, and therefore the area of the quarter circle is the area of the circle of the 4 over 4, that is to say pi R square over 4, minus the area of the small circle, that is pi R square. Okay. So here we take pi over 4 as a common factor from those two expressions. So pi over 4 is a common factor. So what is left from pi over pi is actually pi times capital R square over 4, of course, so the radius of the quarter circle is r squared, therefore the area of the quarter circle equals to the area of the circle, that is pi times capital R over 4. So what is left from pi times capital R squared over 4 after we took from it pi over 4 as a common factor? What is left is actually capital R squared over 4. And what is left from minus pi R squared after we took from it pi over 4 as a common factor? What is left is actually minus 4 times R squared. Why? Because minus 4 times R squared times pi over 4 equals exactly to minus pi R squared. Okay, so here we have already found out that capital R squared minus 4R squared, this expression equals to 64. Therefore, we can substitute this expression. It is actually capital R squared. I repeat again, what is left from pi times capital R squared over 4 after we took from it pi over 4 as a common factor? What is left is actually capital R squared. Okay, and this expression capital R squared minus 4R squared, here it is equal to 64. Therefore, we substitute capital R squared minus 4R squared by 64, and we get that it is equal to the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16, so in total this expression equals to 16 pi. So I found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers it is equal to 50.265 square units. Okay, so we finished with the first method. In the next step, I will present to you how to find out the area of this green shape according to the second method. In the second method, we use all the things that we already found out in the first method. Here we have already found out in the first method that CO equals to 2R. We have already found out that this angle equals to 90 degrees. This is the radius of the small circle, this is also the radius of the small circle. And this angle equals to 90 degrees, of course. In the next step, we'll complete the quarter circle to a circle. Okay. So we completed the quarter circle to a circle. We will extend the radius AO. We already found out in the first method that AO equals to R. It is the radius of the quarter circle and also the radius of the circle itself, of course. We'll extend the radius AO by straight line until it intersects with the circle, and we'll define the touching point of the extended radius AO and the circle as point T. And we'll also extend the straight line CD by straight line until it intersects with the circle, and we'll define the intersection point of the extended line segment DC and the circle as point M. We will join points O and D together by a straight line. Point O is the center of the circle. Point D is the point of the circle itself. Therefore, OD is the radius of this big circle that is equal to capital R. We will join points O and M together by a straight line. So here point O is the center of the big circle, point M is the point of the big circle itself, therefore OM it is also the radius of the big circle that is equal to capital R. Here we extended the straight line DC by straight line, and when you extend a straight line by straight line, the result must be a straight line. So the result is DM, and DM must be also a straight line. Again, DM is a straight line, so I write it down. DM is a straight line. So if we focus on the lower side of the straight line DM at point C, here the sum of the angles must be equal to 180 degrees. So which angles we have at the lower side of MD at point C? We have this angle that is equal to 90 degrees, therefore the missing angle must be also equal to 90 degrees in order to complete the sum of the angles on the lower side of the straight line MD at point C to 180 degrees. This angle must be also equal to 90 degrees. So here we actually, by this construction, we created here two right triangles. Triangle MCO, this right triangle, and triangle, the green right triangle, triangle COD. In the next step, we'll prove that those two right triangles can go into each other. So I write it down. We will prove that the right green triangle, triangle COD, this right triangle, is congruent to the right triangle, triangle MCO. COM. Okay, so why those two right triangles can go into each other? First of all, CO is a common side that belongs to both triangles, so CO equals to itself as a common side that belongs to both triangles. CO equals to CO as a common side that belongs to both right triangles. In addition, we have the hypotenuse MO equals to the hypotenuse OD, and both the radii of the big circle that is equal to capital R, therefore they are equal to each other. So MO equals to OD equals to capital R. So in conclusion, we proved that in those right triangles we have the hypotenuse and one perpendicular that are equal in both right triangles. And therefore we proved that those two right triangles actually can go into each other. And I'll explain you why. When we have a right triangle, it is enough to prove that the hypotenuse and one perpendicular congruent in the two right triangles in order to prove that the two right triangles can go into each other. I will give you an example in order to show you that it is enough to prove that the hypotenuse and one perpendicular is congruent in two right triangles in order to prove that the two right triangles can go into each other. So this is the right triangle ABC. This is the right triangle, triangle DEF. So in those two right triangles, we have the hypotenuse that congruent. Here, the hypotenuse AC equals to the hypotenuse DF. They are both equal to 5 units, therefore they are equal to each other. In addition, we have side AB that is equal to 4 units, and side DE equals also to 4 units. So in those two right triangles, we have the hypotenuse and one perpendicular, they are congruent. Okay, therefore the third side must also congruent. Why? Because according to the Pythagoras theorem, if we focus on the right triangle ABC, side BC will be equal to the square root of 5 square minus 4 square. 5 square is 25, 4 square is 16, and 25 minus 16 is 9, and the square root of 9 is 3. So here we found out that BC equals to 3 units, and here EF will be also equal to the square root of 5 square minus 4 square. Again, 5 square minus 4 square, the square root, it is also equals to 3 units. So here I showed you that if we have two right triangles that have the hypotenuse and one perpendicular that congruent, then the third side must be also congruent. Here BC, the third side is BC, that is equal to 3 units, and it is equal to side EF that is also equal to 3 units. Okay, therefore we prove that the hypotenuse and one side in those two right triangles congruent. Therefore we actually proved that the right triangle, triangle COD, is congruent to the right triangle, triangle COM, according to side rule. Okay. Okay? And because of the fact that those two right triangles can go into each other, we derive from this fact that side DC equals to side CM. Side DC in the green right triangle equals to side CM in the right triangle, triangle OCM. Side DC equals to side CM. Here, side DC equals to side CM according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles can go into each other, therefore the two corresponding sides, that is to say DC and CM, must be also equal to each other. But it is given as the question that DC equals to 8 units. Here, DC equals to 8 units. And from this equation, 8 equals to DC equals to CM, we will derive that CM is also equals to 8 units. Here, CM equals to 8 units. So here, CM equals to 8 units. What is the value, what is the length of AC? From the drawing, it is very easy to see that AC equals to AO minus CO. Again, AO minus CO equals to exactly to AC. So AC equals to AO. AO is the radius of the big circle that is equal to capital R minus CO. CO equals to 2R. So in conclusion, we found out that AC equals to capital R minus 2R. AC equals to capital R minus 2R. What is the length of OT? O is the center of the big circle. T is the point of the big circle itself, therefore OT is the radius of the big circle that is equal to capital R. In the next step, I will present to you rule number 11, and we will implement rule number 11 in our drawing. According to rule number 11, if we have this circle, inside this circle we have chord AB that intersects with chord CD at point O. Again, chord AB intersects with chord CD at point O. Point O is the intersection point of chord AB with chord CD. So if this is the data that has been given to us, then the following equation is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. Okay, we can implement rule number 11 in our drawing. Why? Because in our drawing we have chord AT that intersects with chord MD at point C. Point C is the intersection point of chord AT with chord MD. I repeat again. In our drawing, we have chord AT that intersects with chord MD at point C. Therefore, according to rule number 11, we will get that MC times CD equals to AC times CT. I repeat again, according to rule number 11, we get that MC times CD equals to AC times CT. MC times CD equals to AC times CT. MC equals to 8, CD equals to 8. 8 times 8 is 64. That is equal to AC. AC, what is the value of AC here? AC equals to capital R minus 2R. And what is the value of CT? It is very easy to see from the domain that CT equals to 2R plus capital R. Again, CT equals to 2R plus capital R, or capital R plus 2R. So in conclusion, we found out that according to rule number 11, 64 equals to capital R minus 2R times capital R plus 2R. Here we have the algebraic identity that A plus B times A minus B equals to A squared minus B squared. According to this algebraic identity, here capital R minus 2R times capital R plus 2R. Here in our specific expression, A equals to capital R and B equals to 2R. And A plus B times A minus B equals to A squared minus B squared. So this expression equals to A squared minus B squared. A squared, A is R, so A squared is R squared. A is capital R, therefore A squared is capital R squared minus B squared. B is 2R, therefore B squared is 2R squared. Okay, in conclusion, we found out that 64 equals to capital R squared minus 2R squared. So 64 equals to capital R squared minus 4R squared. Capital R squared minus 2R squared is 4R squared. So in conclusion, we found out that 64 equals to capital R squared minus 4R squared. Okay, and what is the size of the value of the green area? The value of the green area equals its size to the area of the quarter circle minus the area of the small circle. I'll repeat again. The area that we are looking for, that is the area of the green shape, is very easy to see. It is equal to the area of the quarter circle minus the area of the small circle. Okay, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. So, and the area of the quarter circle equals to the area of the circle over 4. The area of the big circle is pi times capital R squared, And if we divide it by 4, we get the area of the quarter circle. Minus the area of the small circle, the area of the small circle equals to pi r squared. So in conclusion, we found out that the green area equals to pi times capital R squared minus pi r squared. Here we will take pi over 4 as a common factor out of those two expressions. So here what is left from pi times capital R squared over 4 after we took from it pi over 4 as a common factor? What is left is actually capital R squared. And what is left from minus pi r squared after we took from it pi over 4 as a common factor? What is left is actually minus 4 r squared. Why? Because minus 4 r squared times pi over 4 equals exactly to minus pi r squared. So here we have already found out that capital R squared minus 4 r squared, capital R squared minus 4 r squared equals to 64. So we substitute this expression capital R squared minus 4 r squared by 64, and we get that the area that we are looking for, the area of the green shape, equals to pi over 4 times 64. 64 over 4 is 16, so in total this expression equals to 16 pi. So we found out that the area of the green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. Okay, so we finished with the second method. In the next step, I present to you the third method. We have already found out in the first method that CO equals to 2R. And this is the radius of the small circle. And this is also the radius of the small circle. We have already found out in the first method that this angle equals to 90 degrees according to rule number 3. I will not repeat on it. We have already found out that AO is the radius of the quarter circle that is equal to capital R. And there we complete the quarter circle to a semicircle. We'll extend the radius AO by a straight line until it intersects with the quarter circle. We'll define the intersection point as point T. Here point O is the center of the quarter circle and also the center of the semicircle, point T is the point on the semicircle itself, therefore OT is the radius of this semicircle that is equal to capital R. Actually here we extended the radius AO, that is a straight line, by a straight line. And when you extend the straight line by a straight line, the result must be a straight line. So here we have the straight line AT that is equal to R, capital R plus capital R is 2R. So the straight line AT is equal to 2 times capital R, and it is passes through the center of the semicircle. So any straight line that passes through the center of the semicircle must be the diameter of the semicircle. That is to say, AT that is equal to 2 times capital R, it is the diameter of the semicircle. It is the diameter of the semicircle. Again, because of the fact that AT is a straight line that passes through the center of the semicircle, it must be the diameter of the semicircle. We can look at AT as a chord that passes through the center of the semicircle. Any chord that passes through the center of the semicircle must be the diameter of the semicircle. So AT is the diameter of the semicircle. Okay. AT is the diameter of the semicircle. In the next step, we'll join points D and T together by a straight line. And we'll join points A and D together by a straight line. Here we actually created peripheral angle ADT. And this peripheral angle ADT rests on AT, that is the diameter of the semicircle. And we actually have rule number 5 that relates to a peripheral angle that rests on the diameter of the circle or semicircle. Here, according to rule number 5, any peripheral angle that rests on the diameter of a circle or semicircle must be equal to 90 degrees. Here we have the peripheral angle AMB. This peripheral angle rests on AB, that is the diameter of this circle. Therefore, peripheral angle AMB equals to 90 degrees according to this rule, rule number 5. So peripheral angle ADT that rests on AT, that is the diameter of this semicircle, it is equal to 90 degrees according to rule number 5. In the next step, we will define angle DTA or ATD as alpha. We will define angle TAD, this angle as beta. And we will focus on the right triangle, the right big triangle, triangle ADT. On the right big triangle, triangle ADT, this angle equals to 90 degrees. So if this angle equals to 90 degrees, the sum of the two other angles must be also equal to 90 degrees. Because 90 degrees plus 90 degrees, it is 180 degrees. That is the sum of the angles in any triangle. So here, the sum of the two other angles is alpha plus beta, and alpha plus beta must be equal to 90 degrees. I write it down. Here, alpha plus beta must be equal to 90 degrees. So here we will subtract beta from this equation, and we'll get that alpha equals to 90 degrees minus beta. In the next step, we'll subtract alpha from this equation. Alpha plus beta equals to 90 degrees, so we'll subtract alpha from this equation, and we get that beta equals to 90 degrees minus alpha. Okay? Here we'll focus on the right small green triangle, triangle ACD. In this right triangle, this angle equals to beta. This angle equals to 90 degrees. Therefore, the missing angle here must be equal to 90 degrees minus beta. Why? Because 90 degrees minus beta plus beta is 90 degrees. Is 90 degrees plus 90 degrees. It is 180 degrees. That is the sum of the angles in any triangle. So I found out that this angle equals to 90 degrees minus beta. But according to this equation, 90 degrees minus beta equals to alpha. So we can substitute 90 degrees minus beta here by alpha. In the next step, we'll focus on the right triangle, triangle CDT. In the right triangle, triangle CDT, this angle equals to 90 degrees. This angle equals to alpha, therefore this angle must be equal to 90 degrees minus alpha. But we have already found out that 90 degrees minus alpha equals to beta, so we'll substitute 90 degrees minus alpha here by beta. And in the next step, we will prove that the right green triangle, triangle ACD, is similar to the right big green triangle, triangle CDT. So I write it down. We prove that the right green triangle, triangle ACD, is similar to the right green triangle, triangle CDT. Okay, so why those two right triangles are similar to each other? First of all, those two angles are both equal to alpha, therefore they are equal to each other. So here angle ADC is equal to this angle that is actually angle CTD. So they are both equal to alpha, therefore they are equal to each other. In addition, those two angles they are both equal to beta, therefore they are equal to each other. So this angle, angle CAD, is equal to this angle that is actually angle CDT. They are both equal to beta, therefore they are equal to each other. And finally, those two angles they are both equal to 90 degrees, therefore they are equal to each other. So angle ACD equals to this angle, that is angle DCT. So they are both equal to 90 degrees, therefore they are equal to each other. So in conclusion, we actually found out that those two right triangles are similar to each other according to angle similarity rule. The right triangle, triangle ACB, is similar to the right triangle, triangle CDT according to angle similarity rule. And for the fact that those two right triangles are similar to each other, we will derive that the following relationship exists between their sides. We will derive that AC in the green right triangle ACD over CD in the green in the right triangle CDT, or AC over CD, equals to CD in the green right triangle ACD over CT. I repeat again, from the fact that the two right triangles are similar to each other, we derive that AC over CD equals to CD over CT. Okay. What is the value of AC? We have already found out in the previous methods that AC equals to capital R minus 2R. So AC equals to capital R minus 2R over CD. CD equals to 8 over 8 CD over CT. What is the value of CT? It's very easy to see from the knowing that CT equals to 2R plus capital R. So in conclusion, according to equation number 1, we found out that capital R minus 2R over 8 equals to 8 over capital R plus 2R. Here we cross multiply this equation, equation number 1, and we will get that according to equation number 1, 8 times 8 is 64, that is equal to capital R plus 2R times capital R minus 2R. So 64 equals to, here, capital R plus 2R times capital R minus 2R. We have already found out in the previous methods that this expression equals to capital R squared minus 4R squared. So in conclusion, we found out that 64 equals to capital R squared minus 4R squared. 64 equals to capital R squared minus 4R squared. Okay. And again, what is the area of the green shape? The area of the green shape is equal to the area of the quarter circle minus the area of the small circle. Repeat again. The area of the green shape equals to the area of the quarter circle minus the area of the small circle. So the area of the green shape equals to the area of the quarter circle, that is pi times capital R squared over 4, minus the area of the small circle, that is pi R squared. Here we took pi over 4 as a common factor, and we have already found out in the previous methods that inside the brackets, here we have capital R squared minus 4R squared. But capital R squared minus 4R squared equals to 64. Here we already found out that capital R squared minus 4R squared equals to 64. Therefore, we substitute capital R squared minus 4R squared in this equation by 64, and we get that the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16, so in total this expression equals to 16 pi. So in conclusion, we found out that the area of the green shape equals to 16 pi square units, so in terms of numbers it is equal to 50.265 square units. Here we finished the third method. In the next step I will summarize the lecture. We start with the first question, of course. In the drawing, we have square ABCD. This is square ABCD. Inside square ABCD, we have a circle. We know that angle CBT, this angle equals to 30 degrees. And we also know that line segment PD equals to 5 units, and our mission is to find out the area of this circle. So first of all, we define the center of this circle as O, and we join points O and Q together by a straight line. OQ is the radius of the circle that is drawn to the point of tendency. Therefore, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. We join points O and P together by a straight line. OP is the radius of the circle that is drawn to the point of tendency. Therefore, this angle equals to 90 degrees, and this angle also equals to 90 degrees according to rule number 1. All the angles inside square ABCD are right angles, so this angle equals to 90 degrees. So inside quadrangle OPQA, we have 1, 2, 3 right angles. The sum of 3 right angles is 270 degrees. Therefore, the fourth angle must be also equal to 90 degrees. In order to complete the sum of the angles in quadrangle OPAQ to 360 degrees, this angle must be equal to 90 degrees. So inside quadrangle OPQA, we have 4 right angles. Therefore, quadrangle OPQA is a rectangle, and you know that the opposite sides of a rectangle are equal to each other. That is to say, PO equals to AQ. PO equals to AQ, but we have already found out that PO equals to R. And from this equation, R equals to PO equals to AQ, we derive that AQ is also equals to R. Here, AQ is equal to R. Likewise, according to the same rule that the opposite sides of a rectangle are equal to each other, we get that AP equals to QO. But QO equals to R. This is the radius of the circle. So from this equation, R equals to OQ equals to AP, we derive that AP is also equals to R. AP equals to R. So we found out that quadrangle AQPO is not a rectangle but a square because all of its sides are equal to R, the radius of the circle. Then we know that in square ABCD, side AD equals to side AB. AD equals to AB. AD equals to R plus 5, and AB equals to R plus QB. So here AD equals to AB in square ABCD, AD equals to 5 plus R, and AB equals to R plus BQ. We subtracted R from this equation and found out that BQ equals to 5 units. Here BQ equals to 5 units. Then I presented to you rule number 2. According to rule number 2, the lengths of two tangents from a common external point to a circle are equal. We have the common external point P. From the common external point P, we have tangent PA and tangent PB. And according to this rule number 2, PA equals to PB. You can implement rule number 2 in our drawing because in our drawing, if we focus on the common external point, point B, from the common external point, point B, we have tangent BQ and tangent BS to this circle, and according to rule number 2, BQ equals to BS. Here, BQ equals to BS. But we have already found out that BQ equals to 5, so we can write here that BQ equals to 5, and from this equation 5 equals to BQ equals to BS, we derive that BS is also equals to 5. Here, BS is also equals to 5. Then we join points O, Q and S together by a straight line. In this way, we created triangle QSB. What is the size of this angle? This angle equals to 90 degrees minus 40 degrees, that is 60 degrees. Here, those two sides, they are both equal to 5, therefore they are equal to each other. And we have the rule that in front of equal sides in the triangle, there are equal angles. So those two angles that are located in front of equal sides must be equal to each other. So if this angle is alpha, this angle must be also equal to alpha because of the fact that those two angles are equal to each other. So here, alpha plus alpha, the sum of those two angles must be equal to 180 degrees minus 60 degrees, that is 120 degrees. So alpha plus alpha equals to 120 degrees. Alpha plus alpha is 2 alpha, that is equal to 120 degrees. We divided this equation by 2 and found out that alpha equals to 180 degrees over 2, that is 60 degrees. So those two angles are both equal to 60 degrees. Therefore, triangle QBS is an equilateral triangle because of the fact that all of its angles are equal to 60 degrees. And we know that in equilateral triangle all the sides are equal to each other. So B equals to 5, BS equals to 5, therefore the missing side QS also must be equal to 5 units. Okay, then we join points O and S together by a straight line. OS is the radius of the circle that is equal to R. We have the radius OS that is drawn to the point of tendency, therefore according to rule number 1, this angle equals to 90 degrees, and this angle also equals to 90 degrees. Okay, then I copied quadrangle QBOS in a new page and we analyze triangle quadrangle QBOS. This is quadrangle QBOS that I copied from the original drawing. We know that the sum of the angles in any quadrangle is equal to 360 degrees. Therefore, 360 degrees minus the sum of the three angles must be equal to the sum of the missing angle. So 360 degrees minus 90 degrees minus 90 degrees minus 60 degrees equals to 220 degrees. So the missing angle equals to 120 degrees. So I found out that this angle equals to 120 degrees. Then I presented to you the law of cosines, and we implemented the law of cosines in the green triangle, triangle QOS. This green triangle, triangle QOS. According to the law of cosines that is true in any triangle, here side AB equals to A, side AC equals to B, and side BC equals to 0 units in its length, and the angle between side AB and side AC is theta. Then, according to the law of cosines, we get that C square equals to A square plus B square minus 2 times A times B times cosine theta. We implemented the law of cosines in this triangle, triangle QOS, that I copied from the original drawing. In this triangle, triangle QOS, according to the Pythagoras theorem, we get that 5 square equals to R square plus R square minus 2 times R minus cosine 120 degrees. Okay, 5 square equals to R square plus R square minus 2 times R times cosine 120 degrees. 5 square is 25, that is equal to R square plus R square is 2R square, and minus 2 times R is minus 2R square, and cosine 120 degrees equals to minus 1/2. We have 2 in the numerator and 2 in the denominator, so 2 will get cancelled, and minus times minus is plus. So in conclusion, found out that 25 equals to 2R square plus R square. 2R square plus R square is 3R square. So in conclusion, found out that 25 equals to 3R square. We divided this equation by 3 and we found out that R square equals to 25 over 3. And the area of any circle is pi R square, and the area of our circle is pi R square. But we have already found out that R square equals to 25 over 3, therefore we can substitute R square in this formula by 25 over 3. We did it when we got that the area of our circle, the area of the circle that we are looking for, equals to pi, and R square is 25 over 3. So the area of the circle equals to either 25 pi over 3 square units, so in terms of numbers it is equal to 50.265 square units. We finished with the first question, then I presented to you the second question, and we solved the second question in 3 different methods. Okay, so here in the drawing we have a quarter circle. Inside the quarter circle we have a small circle. This small circle, we know that line segment CD equals to 8 units, angle ACD equals to 90 degrees, and our mission is to find out the size, the value of the green shape, or the size of the green shape. Okay, so we defined the center of the small circle as J. JE is the radius of the small circle. JF is also the radius of the small circle. According to rule number 1, this angle equals to 90 degrees. According to rule number 1, this angle also equals to 90 degrees. This angle equals to 90 degrees because of the fact that AOB is a quarter circle, and this angle equals to 90 degrees according to rule number 3. Then from point J we draw perpendicular at CO. So this angle equals to 90 degrees and this angle equals to 90 degrees according to our construction. So inside quadrangle CEGT we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. Inside quadrangle TJOF we have 1, 2, 3 right angles, therefore the fourth angle must be also equal to 90 degrees. So we found out that this angle EGF equals to 90 degrees plus 90 degrees, that is 180 degrees. And because of the fact that angle EGF equals to 180 degrees, it means that angle EGF is a straight line. And if angle EGF is a straight line, then line segment EGF is a straight line. And if line segment EGF is a straight line, that line segment EF is also a straight line. And if EF is a straight line, it means that that quadrangle CEOF is a rectangle. Why? Because it has 4 right angles. And we know that the opposite sides of a rectangle are equal to each other. That is to say, EF equals to CO. EF equals to CO in rectangle CEOF. But we have already found out that EF equals to R plus R, that is 2R. So we can write here that EF equals to 2R, and from this equation CO equals to EF equals to 2R, we will derive that CO equals to 2R. Here CO equals to 2R. When we join points O and D together by a straight line, point O is the center of the quarter circle, point D is the point of the quarter circle itself, therefore OD is the radius of the quarter circle, that is equal to capital R according to our definition. Then we implemented the Pythagoras theorem on the right green triangle, triangle COD. According to the Pythagoras theorem, in the right green triangle, triangle COD, the square of the episodes equals to the sum of the squares of the perpendiculars, that is to say, OD square equals to CD square plus CO square. Again, OD square equals to CO square plus CD square. OD is capital R, therefore OD square is capital R square. And it is equal to CO square. CO equals to 2R, therefore CO square is 2R square, that is 4R square, plus CD square. CD equals to 8, therefore CD square is 8 square, that is 64. So I found out that according to equation number 1, R square equals to 4R square plus 64. We subtracted 4R square from this equation and found out that capital R square minus 4R square equals to 64. What is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. And the area of the quarter circle is pi times capital R over 4. The area of the small circle is pi R square. So it is pi times capital R square over 4 minus pi R square. Then we took pi over 4 as a common factor out of those two expressions. What is left from pi times capital R square over 4 after we took from it pi over 4 as a common factor? What is left? It's actually capital R square. What is left from minus pi R square after we took from it pi over 4 as a common factor? What is left is actually minus 4R square, because of the fact that minus 4R square times pi over 4 equals to minus pi R square. This expression capital R squared minus 4R squared, it is equal to 64. Therefore, we substitute this expression by 64 and found out that the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16, so in total this expression equals to 16 pi. So in conclusion, found out that the area of this green shape equals to either 16 pi, or in terms of numbers, it is equal to 50.265 square units. Then I presented to you the second method. In the second method, we found the things that we have only found out in the first method. We have only found out in the first method that CO equals to 2R. And then, and this angle equals to 90 degrees according to rule number 3. Then we completed the quarter circle to a circle. And then we joined points O and D together by a straight line. Point O is the center of the circle, point D is the point of the circle itself, therefore OD is the radius of the circle that is equal to capital R. Then we extended the straight line DC by straight line, and define the touching point of the extended CD in the circle as point M, and we extended the radius AO by a straight line. Point O is the center of the circle, point T is the point of the circle itself, therefore OT is the radius of the big circle that is equal to capital R. Okay, so here we extended the straight line DC by a straight line, therefore the result, that is DM, must be also a straight line. If we focus on the lower side of the straight line DM at point C, here the sum of the angles in the lower side of DM at point C must be equal to 180 degrees. So this angle equals to 90 degrees, therefore the missing angle must be also equal to 90 degrees in order to complete the sum of the angles. In order to complete the sum of the angles in the lower side of DM at point C to 180 degrees, this angle must be also equal to 90 degrees. So we have here two right triangles. The green right triangle DOC and the other right triangle, triangle MCO. We proved that those two right triangles can go into each other. Why those two right triangles can go into each other? Here, first of all, CO is a common side that belongs to both triangles, and DO equals to OM, they are both the radii of the big circle, therefore they are equal to each other. So we proved that the hypotenuse and one perpendicular on those two right triangles can go in, therefore we proved that those two right triangles can go into each other. Why? Because if you have two right triangles that have that can go with each other with the perpendicular and the hypotenuse, then those two right triangles can go into each other. Why? Because the missing third side here, the hypotenuse AC equals to the hypotenuse DF, and the perpendicular AB equals to the perpendicular DE, and the missing side, it is BC and EF, must be equal in both sides, because the missing side, according to the Pythagoras theorem, is equal to the square root of 5 squared minus 4 squared, that is 3. So here EF equals to 3 units and BC equals to 3 units. So according to the Pythagoras theorem, if we have the hypotenuse and the one perpendicular in two right triangles that can go in, then the third side must be also can go in. For that reason, it is enough to prove that one perpendicular and the perpendicular and the hypotenuse can go in those two right triangles in order to prove that the two right triangles can go into each other. So the right triangle COD can go into the right triangle COM according to side rule. Why? Because the third side must also can go in, as I showed you here. So we found out that the two right triangles can go in, Therefore, the two right angles can, and therefore we will derive from it that DC equals to CM according to the rule that corresponding sides in congruent triangles are equal to each other. Those two triangles congruent to each other, therefore the two corresponding sides, that is to say DC and CM, must be also equal to each other. So DC equals to CM, but DC equals to 8 units according to what is given as the equation. So from this equation, 8 equals to DC equals to CM, we derive that CM is also equals to 8 units. Yeah. 8 equals to DC equals to CM, therefore CM is also equals to 8 units. CM equals to 8 units. Then I presented to you rule number 11 and implemented rule number 11 in our drawing. According to rule number 11, if we have this circle and we have chord AB that intersects with chord CD at point O, then CO times OD equals to AO times OB. Again, CO times OD equals to AO times OB. We can implement rule number 11 in our drawing, because in our drawing we have chord AT that intersects with chord MD at point C. Chord AT intersects with chord MD at point C. Therefore, according to rule number 11, we get that MC times CD equals to AC times CT. Again, according to rule number 11, we get that MC times CD equals to AC times CT. MC equals to 8 and CD equals to 8 also, so MC times CD is 8 times 8, that is 64. AC equals to capital R minus 2R, and CT equals to 2R plus capital R. So in conclusion, found out that 64 equals to capital R minus 2R times capital R plus 2R. So 64 equals to this expression. We already found out that the value of this expression equals to capital R squared minus 2R squared. That is to say 64 equals to capital R squared and minus 2R squared is minus 4R squared. So in conclusion, we found out that 64 equals to capital R squared minus 4R squared. And what is the area of the green shape? The area of the green shape equals to the area of the quarter circle minus the area of the small circle. Again, the area of the green shape equals to the area of the quarter circle minus the area of the small circle. The area of the quarter circle equals to pi times capital R squared over 4, and the area of the small circle equals to pi R squared. We took pi over 4 out of those two expressions as a common factor, so inside the brackets we left with only capital R squared minus 4R squared. But this expression, capital R squared minus 4R squared, it is equal to 64. Therefore, we can substitute this expression by 64. We did it and we got that the area of the green shape equals to pi over 4 times 64. 64 over 4 is 16. So in total, this expression equals to 16 pi. So we found out that the area of the green shape, according to the third method, it is equal to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. So, in all three methods, we found out that the area of this green shape equals to either 16 pi square units, or in terms of numbers, it is equal to 50.265 square units. Okay? Thank you very much.